Welcome to section 2.6, related rates. Today it's going to be talking about using the chain rule and implicit differentiation together to find the rates of change with respect to time. We're going to be finding derivatives of functions with variables that we do not know and do not see. So I think the easiest understanding of why we're doing this is with this kind of diagram, and hopefully it's going to make sense. So we are finding the volume of a conical tank. We know the radius is a certain value and the height is a certain value. Over time, as the water trickles out, the height has to change because you're not going to have as much water in the tank. And if the height is a different height, your radius has to change because that's how the shape of a cone works. So over time, your height changes, your radius changes, and we know the volume is based off of your radius and your height with this formula right there. So over time, the volume also changes. So all three variables, the volume, the radius, and the height, are all actually going to be functions of t. So we're going to take the derivative of everything with respect to t. So dv dt is the derivative of v with respect to t. That one's a little bit easy. But then we have a product rule. So when we're taking the derivative, the first variable, if you want to call it that, is r, but we're taking that as a function of t, so we have to take the derivative of that function r with respect to d. That's the dr dt, and then the same thing with the dh dt. So now we have an equation to figure out what the rate of change of the volume is with respect to time. Over time, we're going to have less water, and we'll be able to figure out how much the volume actually is. Now we're going to start with actually calculating an easier related rate, an easier problem. We'll get to more complicated ones. So it says, suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when all that other stuff happens. Now, I know that when we did implicit differentiation before, we treated everything as an x and did dy dx, and that was that. But now we're taking the derivative with respect to t. So derivative of y with respect to t is dy dt. The derivative of x, we used first the power rule, but then we have to multiply by the derivative of x with respect to t. Okay, because x is a function of t, it's not a function of x anymore. And then the derivative of 3 is 0, derivative of a constant is always 0. And now we plug in what we know. I don't know dy dt, that's what I want to find anyway. I know that x is going to be 1 and dx dt is going to be 2 whenever x is 1. So since x is 1, dx dt is 2. So I'm now able to see that the derivative of y with respect to time is equal to 4. Example 2, we've got a pebble being dropped into a pond, and it causes ripples that form concentric circles. So if we remember first what concentric circles are, if you're able to draw better circles than me, that's awesome. It's just a bunch of circles that have the exact same center point, and we are going to be worried about the radius to the outer circle. So the radius of the outer ripple is increasing at a constant rate of 1 foot per second. When this radius is 4 feet, at what rate is the total area of the disturbed water increasing? So first, let's remember the area formula for a circle. And then let's figure out what we're trying to find. Well, we want to know what dA dt is. We want to know what the rate of the area with respect to time is. We do already know that we're talking about when the radius is 4 feet, and we know dr dt is 1 foot per second. Okay, the radius is increasing at a constant rate of 1 foot per second. So now we go ahead and take the derivative of all this stuff. Derivative of a with respect to time is dA dt. Pi is just a constant, so I don't really worry about it. It's not a standalone constant, so it doesn't become 0 when I take the derivative. I'm going to take 2 pi r. That would be the derivative if the function was of just r, but the derivative of r with respect to time would be dr dt. So now I can plug in the things that I know. I know that the radius is 4 feet and dr dt is 1 foot per second. So that tells me that dA dt is going to be 8 pi. I'm going to need a label here. my label is going to be square feet per second. Getting that label is something that you may or may not struggle with. One way that you can help would be to put your labels in the problem. So I'm going to come back here, and I know that this was 4 feet, and I know this is 1 foot per second. And then you can treat those labels kind of like fractions and such. Feet times feet gives you the feet squared. We only have a second to the first power on the bottom. That can be how we get our label. So the process for solving related rate problems. First, you need to define variables for all the given quantities to be determined. Make a sketch, label the quantities if that's even possible, or if it's feasible. Like if you had to draw 1,000 circles, you can do it. That's possible, not feasible. Write an equation involving the variables whose rates of change either are given or we need to find. And then use the chain rule to implicitly differentiate both sides of the equation with respect to time, then substitute in the things that we know in order to figure out the thing that we want to know. For the next one, we have air being pumped into a spherical balloon at a specific rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. So the volume of a sphere is 4/3 pi r cubed. So if I want to find my related rate, before I even worry about that, I'm going to write off to the side what we already know. We know that the volume is changing at a constant rate of 4.5 inches cubed per minute. If we were deflating this same balloon, we would subtract 4.5 because it'd be getting smaller. We don't know what the derivative of r with respect to time is. That's what we're trying to find. But we know that that's going to be when the radius is equal to 2. So back to this blue function. Derivative of v with respect to time is dv dt. 4/3 pi is a constant times r cubed. So when I do my power rule, I'm going to bring the 3 down. That's going to leave me with 4 pi, because 4/3 times 3 is 4. Pi is pi. R squared times dr dt, because radius is a function with respect to time. So now I can plug in the things that I know. I know dv dt is 4.5 inches cubed per minute. I have 4 pi, the radius is 2, should have put inches here, 2 inches squared, and then I put a fraction, I didn't need a fraction, dr dt. This is now algebra. You can solve it kind of either order that you want to. I'm going to first multiply out the right-hand side as far as I can, where that 2 squared is 4, times 4 is 16 pi, and then inches squared is inches squared, dr dt. Now I divide both sides by 16 pi inches squared. All right, I'm going to put this inches squared bit, that whole thing, in parentheses. Inches squared is not technically the multiplication, it's just how I can group my labels so I know I end up with the right one. But I should have 4.5 inches cubed per minute divided by 16 pi inches squared equal to dr dt, and now I can simplify this. So in my calculator, I'm just going to do 4.5 divided by 16. I'm going to hit enter, and then I'm going to hit divide by pi. The reason I'm doing that is so I make sure that I get pi in the denominator, because if I just hit 4.5 divided by 16 times pi with no parentheses, that would put pi in the numerator. So you just got to make sure we're careful with our order of operations. So that's going to be 0.0895, and I'm just going to round it to that point and call it good. My label, I have inches cubed on top and inches squared on bottom. That leaves inches on top, and then per minute. Minutes didn't have anything to change. So the derivative of the radius with respect to time, the rate of change of the radius with respect to time is 0.0895 inches per minute. For this next one, we have a sand and gravel pit. Sand's falling off of a conveyor belt onto a conical pile at a rate of 10 cubic feet per minute. The diameter of the base is approximately 3 times the altitude. So I'm going to draw my picture first. So when I'm drawing a cone, I'm basically going to draw an oval and bring it up to a point. I have a height, which goes to the center of that circle, and I have a radius. So there's my height, and there's my radius. The diameter of the base, I know diameter is just 2 times r. So off to the side, the things that I don't know and things that I want to know, because it says at what rate is the height of the pile changing. So I'm trying to find dH dt, but I know the volume is changing at a rate of 10 feet cubed per minute. That's what it tells me, cubic feet. I know that 2r is equal to 3h. I get that because the diameter is approximately 3 times the altitude, which I named as h. And instead of diameter, I put 2r. That tells me that r is equal to 3h over 2. And I know that this is happening when h equals 18 feet. So, volume function for a cone is 1/3 pi r squared h. That's why I wanted to come back into radius instead of diameter. To take my derivative, I'm going to have 2 pi thirds r dr dt times h plus, I'm going to make my life easier. I could do that. What I was doing is I was starting to do the chain rule, but I know what r is in terms of h, so I can make my life significantly easier by replacing r with h. So now when I multiply that out, I'm going to have a total of 3 h's in the top. So I'm going to have 3 pi h cubed over 2. It could have been a 9 pi h cubed over more than that. Oh, should have been over 4, excuse me. Forgot to square the bottom. That's bad of me. I canceled some 3's, so I have this 3 cancels one of those 3's. That's why I get the 1 3 left on top. H squared times h is h cubed. 2 squared on the bottom is a 4. So now dv dt is going to be a little bit easier because I only have to worry about h for my implicit differentiation. When I do this, I'm going to get 9 pi h squared over 4 times dh dt. And I'm trying to find dh dt, and I know all of the rest of those variables. I'm going to plug them in. So dv dt is 10 feet cubed per minute. Then I have 9 pi, and then my height is 18 feet all over 4. I can simplify this if I want to. If I don't want to, I don't have to. I'm going to go through and I know that I can't get rid of the 4 completely, so I'm not going to worry about simplifying. Okay, but I know that I have 40 feet cubed per minute is equal to, well, 9 times 18 is 162, and then there's pi feet. When I divide both sides, I lost my dh dt here. That's bad because that's what I'm trying to find. When I divide both sides by 162 pi feet, I'm going to take 40 divided by 162 equals divided by pi equals, and that is going to give me, I think I made a mistake somewhere. Nope, that looks good. So I'm going to get 0.0785. I'm going to round this up to a 6 because it was 0.5 or 0.078595. So I'll go to 6. I had 2 of the feet left on top, minute on bottom. So derivative of height with respect to time. All I'm doing, I did make a mistake. I found it. Sorry. My mistake was I lost my squared. So instead of 162 pi, I had 2916. All right. something felt wrong, and I went and found it. So I'm dividing by 2,916 pi feet. All right, so sorry about that. 40 divided by 2,916 equals, divided by pi equals, that looks more correct to me, 0.0044, I'll round it to, but my label is still feet squared per minute. Now, I had kind of quickly glanced and thought I had made a mistake, and I didn't, or thought I didn't, so I went back and I just kept working. What tipped me off at the end was when I got my answer and I made sure my labels were feet squared, and I was like, wait, squared, how come I have squared? Oh yeah, so I have this piece right there. My labels made a mistake, and the labels helped me catch it. So why did I have it squared? Because the height shouldn't be a squared unit. This should have been a squared, this should have been a squared, that should have been a squared. So we get just feet per minute. I made like a handful of mistakes in that problem, but I can catch them if I think about what we're talking about. So the change in height with respect to time. Height is a linear measurement, so at the end, I should have a linear label. Working with your labels like this can help you catch those mistakes. If you are someone who's like, I'm super good at, I never make mistakes ever, which is a lie, and you just put the correct label on at the end, you might miss a mistake that you made that you would have caught otherwise had you used your labels. All right. Now, this next one, hopefully I don't make any mistakes, and we'll go from there if I do. So, the rate of change of the distance between the origin and a moving point on the graph of x squared plus 1. Off to the side, I'm going to draw a quick sketch of x squared plus 1. All right. My origin is here, and then I'm going to have some point there, and I'm finding that distance. So my distance formula, that's just my Pythagorean theorem, but square root on both sides, is the change in x's squared plus the change in y's squared, all under a square root. So I know my origin is 0, 0, and I know that I'm looking at the point x squared plus 1. All this point is telling me where that dot right there is. If I plug in x, what is the output of that? Okay, so what I'm going to do is I'm going to generalize this distance formula by plugging in my origin and these ordered pairs. So I'm going to have the 0, 0 being my x1, y1 because it just makes my life easier. So I've got x minus 0 squared plus, and that x comes from this x. So now instead of y2, I'm going to have x squared plus 1 minus 0 squared. I'm going to continue to get x squared plus, and then I have x squared plus 1 squared, which is going to give me x to the 4th plus 2x squared plus 1. I can combine some like terms there. I've got square root of x to the 4th plus 3x squared plus 1. Now, I don't want to have the square root involved, so instead I'm going to write it with an exponent of 1/2. Now I'm able to take the derivative of this. I can use my power rule, so d dt is going to be 1/2 times the stuff on the inside to the negative 1/2 times that whole thing with respect to time. Well, if I'm multiplying by the derivative of the inside now for my chain rule, that's going to give me a 4x cubed dx dt plus 6x dx dt, and then plus 0 dx dt for the plus 1 piece. So I had to do the derivative of the outside times the derivative of the inside. So now when I go through to kind of simplify this a little bit, I'm just going to plug in the values that I know. So I'm looking at dx dt is 4 when x is equal to 1. So instead of multiplying all that stuff out, I'm just going to plug in the values that I care about. So 3x squared is 3 times 1 squared plus 1 is still plus 1. Then I've got 4 times 1 cubed times my dx dt is 4. So 6 times 1 times 4. Now if I multiply this out, I would probably just do this on my calculator. If you want to try to simplify this and have a positive exponent, you can. I just know that inside of this parentheses is a 5, and I'm going to be taking the square root of it on the bottom. I know inside here I've got 16 plus 24, that's going to be 40. So I actually have 1/2 times 1 over root 5 times 40. That would be what I'm plugging in. Because my handwriting is large and sloppy, I've kind of went on to the next slide, and it is what it is. To plug this into my calculator, I'm going to do 1 divided by square root 5 first, actually, because that's easier for me for whatever reason. Because I can divide by 2, multiply by 40, and we're going to get 8.9443. All right. And it says find the rate of change of the distance. My label would just be units. Okay, I can put units if I want to. I'm just going to leave it like this for right now. That's a terrible box. And there we go. Number 6 is kind of like a classic problem that you'll see in calculus a lot. Is you have a ladder leaning on a wall, and the bottom is going to start to slide away. So, drawing a quick picture, we're going to assume our walls are perfectly vertical, and then we have a ladder going like this. I'll label this X, this Y, and then my ladder is 13 feet, so I'm going to put a 13 feet there. The Pythagorean Theorem tells me that x squared plus y squared is equal to 13 squared. I know this is supposed to be a right angle because that's how we set it up. We're assuming the walls are perfectly vertical. It says the base of the ladder is sliding away from the wall at a rate of 1.5 feet per second. The base is going to be by x, so the rate of change of x is going to be dx dt, and we're going away 1.5 feet per second. As this base slides out, x is going to get larger, so that's why it's positive. So I should be assuming that whatever I get for dy dt is going to be a negative, because as the ladder slides away from the wall, the top is not going to be as high on the wall, so that y value should shrink. And I know that x is going to be 5 feet, because that's what it's asking for specifically. So if I go to take the derivative of that function right there, I'm going to have 2x dx dt plus 2y dy dt equals 0, because the derivative of that is going to be 0. I don't even care to multiply it out. I don't need to. All right. So now I want to figure out what the y value of this triangle is going to be at x equals 5, so I'm able to plug a number in for y. Well, if I have x squared is 5, I need this to be true. If you remember your Pythagorean triples, you can know that y is 12. Otherwise, you'd have to take 169 minus 25 and square root both sides. But now I can plug stuff in. So I've got 2 times 5 times 1.5. I should have put a feet label here and a feet per second label there. Plus 2 times 12. My label for y is still going to be feet as well. And then dy dt is equal to 0. When I multiply this thing out, I actually am just going to end up with 15 feet squared per second plus 24 feet times dy dt equals 0. When you go to solve this, you're going to subtract that value over. So we're on track to get that negative I was talking about. And then I divide both sides by 24 feet to get the dy dt. The feet squared divided by feet is going to be left with feet per second, which is good because the y value should be linear. So if I take 15 divided by 24, I can simplify that to 5/8. But I had a negative sign, so I need to have a negative sign there as well. As a fraction, I could leave it like that. If I wanted to put a decimal, I could put a decimal. It's a nice terminating decimal. All right, we've got 2 more problems, it looks like. Hopefully these are going to go a little bit quicker, even though they're a little bit involved. So, airplane is flying at an elevation of 6 miles on a flight path that will take it directly over a radar tracking station. I'm going to draw myself a triangle here. This is where the plane is. This is the tracking system. And we're 6 miles for elevation. And then I want to know, it says let S represent the distance in miles between the plane and the radar station. So that's the hypotenuse. And then I can say this is X. Pythagorean Theorem, again, I've got 6 squared plus X squared is equal to S squared. I know that dx dt is the velocity of the plane, and that's what I'm asking for, so I don't know what it is. I know that S is going to be 10 miles, and I know that ds dt is going to be, well, it's decreasing at a rate, so subtract negative 400 miles per hour. Related rates, I've got 0 plus 2x dx dt is equal to 2s ds dt. Plug in the things that we know. I know that x is going to be 8 miles at this point. The reason I know it's 8 miles is because I have notes that I'm looking at that I've done off to the side. How did I get 8 miles is, well, when s is 10, I make a new triangle. I have 6 miles squared plus x squared equals 10 squared. All right, so if I find that, that's going to tell me that x is equal to 8. And then dx dt, we didn't know, but that's equal to 2 times 10 times negative 400 miles per hour. I should have put miles with that 10, but I forgot. So I've got 16 miles times dx dt is equal to negative 8,000 miles squared per hour. Divide both sides by 16 miles. I've got dx dt is equal to, well, negative 8,000 divided by 16 is going to be negative 500. Miles squared divided by miles is miles, and hours is by itself. So that is my rate of change of x with respect to time. It's getting smaller because as time goes by, that plane is flying directly overhead of that radar station. Okay, and then one more. We've got some trig now. So a TV camera is at ground level filming the liftoff of a space shuttle, and the position function is given to us as s equals 50t squared. That's how the plane is rising, or the space shuttle is rising. We are having a triangle where S is right there, and we are going to be 2,000 feet away. And we want to figure out the rate of change, the angle of elevation. So I'm going to have theta right there. I'm going to have 10 seconds after liftoff, and I'm looking for the derivative of theta with respect to time. Hopefully from geometry, we can remember that tangent of theta is opposite over adjacent. But I know what S is, so I can plug that in. And I can simplify that a little bit to t squared over 40. To take my derivative, the derivative of tangent is going to be secant squared theta, but now I need times d theta dt, equals the derivative of the right-hand side. I don't need a d something dt because I actually have a function of t. So that's going to just be 2t over 40, or t over 20. Secant squared is 1 over cosine squared, so if I multiply both sides by cosine squared, I'm going to get t cosine squared theta over 20. And now I need to figure out at time, when time is 10 seconds, what is that angle going to be? So I'm going to draw a triangle off to the side here. I know that the camera is still 2,000 feet away. I know that at 10 seconds I have, based off of this function right here, I have 50 times 10 squared, which is going to be 5,000. If you use your Pythagorean theorem, you're going to get 290, 0, 0, 0. I gotta make sure I count the right number of zeros here. 1, 2, 3, 4, 5, 6 zeros. Oops, terrible comma placement. That's why I hate commas. So I have 1, 2, 3, 4, 5, 6 zeros, square root of 29 million. So cosine of this angle at that point is going to be 2,000 over that massive square root of 29 million. So I can plug that in. D theta over dt is equal to 10 times 2,000 over the square root of 29 million squared all over 20. If I plug that into my calculator, it takes me a little time to plug in my calculator, but I should get 0.0690. We measure our angle in radians per second. That problem was kind of brutal. That's one that you definitely are probably going to want to ask about in class. We can go through it more specifically together. All right. There are your homework problems. You don't have to do all of them in one sitting. I recommend not doing that all in one sitting. That'd be kind of brutal. But I hope everybody has a great day.